Binary Star, Part 1 of 2, from Wikipedia, the free encyclopedia, http://en.wikipedia.org. A binary star system consists of two stars both orbiting around their center of mass. For each star, the other is its companion star. Recent research suggests that a large fraction of the stars are part of systems with at least two stars. Binary star systems are very important in astrophysics. The masses of many single stars are determined by extrapolations made from the observation of binaries. Binary stars are not the same as optical double stars, which appear to be close together as seen from Earth, but are in reality not bound by gravity. Binary stars can either be distinguished optically, visual binaries, or by indirect techniques such as spectroscopy. If binaries happen to orbit in a plane perpendicular to our line of sight, it is possible for them to eclipse each other. These are called eclipsing binaries. The components of binary star systems can exchange mass, bringing their evolution to stages that single stars cannot attain. Examples of binaries are Algol, an eclipsing binary, Sirius, and Cygnus X1, of which one member is probably a black hole. Section 1. Terminology. The term binary star was coined by Sir William Herschel in 1802 to designate, in his definition, a real double star, the union of two stars that are formed together in one system by the laws of attraction. Any two closely spaced stars might appear to be a double star, the most famous case being Mizar and Alcor in the Big Dipper. It is, however, possible that a double star is merely a star pair that only looks like a binary system. The two stars can in reality be widely separated in space, but just happen to lie in roughly the same direction as seen from our vantage point. Such false binaries are termed optical binaries. With the invention of the telescope, many such pairs were found. Herschel, in 1780, measured the separation and orientation of over 700 pairs that appeared to be binary systems, and found that about 50 pairs changed orientation over 2 decades of observation. A true binary is a pair of stars bound together by gravity. When they can be distinguished, with a powerful enough telescope, if necessary with the aid of interferometric methods, they are known as visual binaries. In other cases, the only indication of binarity is the Doppler shift of the emitted light. Systems in which this is the case, known as spectroscopic binaries, consist of relatively close pairs of stars where the spectral lines in the light from each one shifts first toward the blue, then toward the red, as it moves first toward us and then away from us, during its motion about their common center of mass, with the period of their common orbit. If the orbital plane is very nearly along our line of sight, the two stars partially or fully occult each other regularly, and the system is called an eclipsing binary, of which Algol is the best known example. Binary stars that are both visual and spectroscopic binaries are rare, and are a precious source of valuable information when found. Unless they are relatively close to Earth, visual binary stars have a large true separation, and consequently usually have orbital speeds too small to be measured spectroscopically. Conversely, spectroscopic binary stars move fast in their orbits because they are close together, usually too close to be detected as visual binaries. Binaries that are both visual and spectroscopic are thus usually relatively close to us. Scientists have discovered some stars that seem to orbit around an empty space. Astrometric binaries are relatively nearby stars which can be seen to wobble around a middle point with no visible companion. With some spectroscopic binaries, there is only one set of lines shifting back and forth. The same mathematics used for ordinary binaries can be applied to infer the mass of the missing companion. The companion could be very dim, so that it is currently undetectable or masked by the glare of its primary, or it could be an object that does not emit any electromagnetic radiation, like a neutron star. In some instances, there is strong evidence that the missing companion is in fact a black hole, a body with such strong gravity that no light is able to escape. Such binaries are known as high-mass X-ray binaries. Probably the best-known example at present is Cygnus X1, where the mass of the unseen companion is believed to be about 9 times that of our Sun, far exceeding the maximum theoretical mass of a neutron star, the only other likely candidate for the companion. In this way, Cygnus X1 became the first object that was widely accepted as being a black hole. Section 2. Classifications. By methods of observation. Binary stars are classified into 4 types according to their observable properties. Any binary star can belong to several of these classes. For example, several spectroscopic binaries are also eclipsing binaries. Visual binaries. A visual binary star is a binary star for which the angular separation between the 2 components is great enough to permit them to be observed as a double star in a telescope. The resolving power of the telescope is an important factor in the detection of visual binaries, and as telescopes become larger and more powerful, an increasing number of visual binaries will be detected. The brightness of the 2 stars is also an important factor, as brighter stars are harder to separate due to their glare than dimmer ones are. The brighter star of a visual binary is the primary star, and the dimmer is considered the secondary. The position angle of the secondary with respect to the primary is measured, together with the angular distance between the 2 stars. The time of observation is also recorded. After a sufficient number of observations are recorded over a period of time, they are plotted in polar coordinates with the primary star at the origin, and the most probable ellipse is drawn through these points such that the Keplerian law of areas is satisfied. This ellipse is known as the apparent ellipse, and is the projection of the actual elliptical orbit of the secondary with respect to the primary on the plane of the sky. From this projected ellipse, the complete elements of the orbit may be computed, with the semi-major axis being expressed in angular units unless the stellar parallax, and hence the distance of the system, is known. Spectroscopic binaries. A spectroscopic binary star is a binary star which cannot be resolved as a visual binary, even with telescopes of the highest existing resolving power. In such binaries, the separation between the stars is usually very small, and the orbital velocity very high. Unless the plane of the orbit happens to be perpendicular to the line of sight, the orbital velocities will have components in the line of sight, and the observed radial velocity of the system will vary periodically. Since radial velocity can be measured with a spectrometer by observing the Doppler shift of the star's spectral lines, the binaries detected in this manner are known as spectroscopic binaries. In some spectroscopic binaries, the spectra of both stars are visible and the lines are alternately double and single. Such stars are known as double-line binaries. In others, the spectrum of only one of the stars is seen, and the lines in the spectrum move periodically from blue to red and back again. The orbit of a spectroscopic binary is determined by making a long series of observations of the radial velocity of one or more component of the binary. The observations are plotted against time, and from the resulting curve a period is determined. If the orbit is circular, then the curve will be a sine curve. If the orbit is elliptical, the shape of the curve will depend on the eccentricity of the ellipse and the orientation of the major axis with reference to the line of sight. It is impossible to determine individually the semi-major axis A and the inclination of the orbit plane I. However, the product of the semi-major axis and the sine of the inclination, that is, A sine I, may be determined directly in linear units, for example, kilometers. If either A or I can be determined by other means, as in the case of eclipsing binaries, a complete solution for the orbit can be found. Eclipsing binaries. An eclipsing binary star is a binary star in which the orbit plane of the 2 stars lies so nearly in the line of sight of the observer that the components undergo mutual eclipses. In the case where the binary is also a spectroscopic binary and the parallax of the system is known, the binary is quite valuable for stellar analysis. Eclipsing binaries are variable stars, not because the light of the individual components vary, but because of the eclipses. The light curve of an eclipsing binary is characterized by periods of practically constant light, with periodic drops in intensity. If one of the stars is larger than the other, one will be obscured by a total eclipse, while the other will be obscured by an annular eclipse. The period of the orbit of an eclipsing binary may be determined from a study of the light curve, and the relative sizes of the individual stars can be determined in terms of the radius of the orbit by observing how quickly the brightness changes as the disk of the near star slides over the disk of the distant star. If it is also a spectroscopic binary, the orbital elements can also be determined, and the mass of the stars can be determined relatively easily, which means that the relative densities of the stars can be determined in this case. Astrometric binaries. An astrometric binary star is a binary star for which only one of the component stars can be visually observed. The visible star's position is carefully measured and detected to have a wobble due to the gravitational influence from its counterpart. The position of the star is repeatedly measured relative to more distant stars, and then checked for periodic shifts in position. Typically, this type of measurement can only be performed on nearby stars, such as those within 10 parsecs. Nearby stars often have a relatively high proper motion, so astrometric binaries will appear to follow a sinusoidal path across the sky. If the companion is sufficiently massive to cause an observable shift in position of the star, then its presence can be deduced. From precise astrometric measurements of the movement of the visible star over a sufficiently long period of time, information about the mass of the companion and its orbital period can be determined. Even though the companion is not visible, the characteristics of the system can be determined from the observations using Kepler's laws. This method of detecting binaries is also used to locate extrasolar planets orbiting a star. However, the requirements to perform this measurement are very exacting due to the great difference in the mass ratio and the typically long period of the planet's orbit. Detection of position shifts of a star is a very exacting science, and it is difficult to achieve the necessary precision. Space telescopes can avoid the blurring effect of the Earth's atmosphere, resulting in more precise resolution. Biconfiguration of the system. Another classification is based on the distance of the stars relative to their sizes. Detached binaries are a kind of binary stars where each component is within its Roche lobe, that is, the area where the gravitational pull of the star itself is larger than that of the other component. The stars have no major effect on each other and essentially evolve separately. Most binaries belong to this class. Semi-detached binary stars are binary stars where one of the components fills the binary star's Roche lobe and the other does not. Gas from the surface of the Roche lobe filling component, donor, is transferred to the other star, accretor. The mass transfer dominates the evolution of the system. In many cases, the inflowing gas forms an accretion disk around the accretor. Examples of this type are X-ray binaries and cataclysmic variable stars. A contact binary is a type of binary star in which both components of the binary star fill their Roche lobes. The uppermost part of the stellar atmospheres forms a common envelope that surrounds both stars. As the friction of the envelope breaks the orbital motion, the stars may eventually coalesce. This concludes Part 1 of Binary Star. This sound file and all text in the article are licensed under the GNU Free Documentation License, available at www.gnu.org/copyleft/fdl.html.